students. Now in this video let us see few more examples on the same divisibility and the GCD property here. So example on Euler's theorem and Fermat's theorem also we are using there. So the example that show that n raised to 12 minus a raised to 12 is divisible by 91 if n and a are prime to 91. Solution: given that n and a are prime to 91, that is n and 91 their GCD is 1 and a and 91 this GCD is also what? 1. But 91 is not prime, that's why we are unable to apply the Euler's theorem here. That's why we should write 91 as a prime factorization. So we can write it as, I can say, but 91 is equal to what? 7 into 13. Therefore to show 91 divides n raised to 12 minus a raised to 12. It is enough to show what? 7 divides n raised to 12 minus a raised to 12 and 13 divides n raised to 12 minus a raised to 12. This is a part. Fine. So now let us start for that. So now 7 is prime. 7 is a prime and 7 and n, the GCD of 7 and n, and obviously GCD of n and a are what? 1, whatever n and a are they. Fine. So now therefore by Euler's theorem, what can we say? N raised to 5 of 7, n raised to 5 of 7 congruence to whom? 1 modulo 7 and a raised to 5 of 7 congruence to what? 1 modulo 7. Fine. Okay. So what does this gives? This gives n raised to 6 congruence to 1 modulo 7 and what? A raised to 6 congruence to 1 modulo 7. Why does this? Since 5 of 7 is what? 6. This is a reason for this step. Fine. So what does this says? This gives 7 divides n raised to 6 minus 1 and 7 also divides a raised to 6 minus 1. So this gives 7 divides n raised to 6 minus 1 into n raised to 6 plus 1 and 7 divides a raised to 6 minus 1 into a raised to 6 plus 1. Okay. That is same as to say 7 divides n raised to 12 minus 1 and 7 divides a raised to 12 minus 1. Fine. So what does this says? This gives n raised to 12 congruence to 1 modulo 7 and a raised to 12 congruence to 1 modulo 7. Okay. So now from these two congruences we can write, therefore n raised to 12 minus a raised to 12 congruence to what? 0 modulo 7. So this gives 7 divides what? N raised to 12 minus A raised to 12. So we have improved this first part. Fine. Now we have to simply show 13 divides N raised to 12 minus A raised to 12. Okay. So for that now 13 is prime. 13 is prime. Call it as equation number 1 suppose. 13 is prime and N and 13 and A and 13 are what? Relatively prime. Fine. Relatively prime. This is their GCD is what? 1. Fine. Therefore, N raised to 5 of 13 congruence to what? 1 modulo 13 and A raised to 5 of 13 congruence to 1 modulo 13. Okay. So N raised to 5 of 13. So it will be N raised to 12 congruence to 1 modulo 13 and A raised to 12 congruence to 1 modulo 13. Since 5 of 13 is what? 12. This is the reason for this step. Fine. Now therefore, now take this subtraction here again. N raised to 12 minus A raised to 12 congruence to what? 0 modulo 13. Therefore, this gives 13 divides N raised to 12 minus A raised to 12. Call it as equation number 2. Therefore, from 1 and 2, we get 91 divides N raised to 12 minus A raised to 12. This is the answer of this question. Fine. Now let me go for the next question. Next example is that show that N raised to 6k minus 1 is divisible by 7 if N and 7 are relatively prime and k is any positive integer. K is from Z plus. Okay. So solution, given that what? N and 7 are relatively prime, and what is our claim? Our claim is that we have to show 7 divides N raised to 6k minus 1. Fine. So here this N raised to 6k minus 1 can be written as N raised to 6 raised to k minus 1 raised to k. So now this can be factorized as N raised to 6 minus 1 into N raised to 6 raised to k minus 1. This is using binomial expansion. Fine. And N raised to 6 raised to k minus 2. From binomial we can obtain this result to factorize this one, plus N raised to 6 raised to k minus 3 plus so on plus 1. Fine. So therefore, by Euler's theorem, what we get? N raised to 5 of 7 congruence to what? 1 modulo 7. Sorry, this will be here. It is congruence to base 1 modulo 7. We should write it in detail. So this gives us N raised to 6 congruence to what? 1 modulo 7. Since 5 of 7 is what? 6. Okay. Therefore, this gives 7 divides n raised to 6 minus 1. So this gives 7 divides n raised to 6 minus 1 into this bracket also. We can take this bracket as x. Fine. So n raised to 6 raised to k minus 1 plus n raised to 6 raised to k minus 2 plus n raised to 6 raised to k minus 3 plus so on plus 1. Okay. So this gives 7 divides n raised to 6k minus 1. As such we can prove this. Fine. Now the next example. Write a single congruence. Write a single congruence that is equivalent. Write a single congruence that is equivalent to the pair of the congruences. X congruence to 1 modulo 4 and x congruence to 2 modulo 3. Okay. Now solution. Given that, what is given to us? We have to write these two congruences in a single congruence which is equivalent to both of them. So now what is given to us? Only two congruences are given to us. So x congruence to 1 modulo 4 and x congruence to 2 modulo 3. Okay. So let me use this. So as x congruence to 1 modulo 4, so by the definition of congruence we get this one gives 4 divides x minus 1. So now as 4 divides x minus 1, so this is equivalent to write as x minus 1 is equal to 4 into k. Here k is any integer. It is using the definition of divisibility. Fine. So this is same as to say x is equal to what? 4k plus 1, where k is what? An integer. Fine. Again what is with us? X congruence to 2 modulo 3. So now this can be written as, now these x's are same. So this x can be replaced by 4k plus 1 from this. So this can be written as 4k plus 1 congruence to what? 2 modulo 3. Okay. That is same as to say, this is same as to say 4k congruence to what? 1 modulo 3. We have been subtracted 1 here. Fine. So here this 1 is left only. Fine. So this is same as to say what? K congruence to what? 1 modulo 3. As 4k congruence to 1 modulo 3, so k also congruence to 1 modulo 3. So this gives 3 divides what? K minus 1. Therefore k minus 1 is equal to what? 3 times some new integer. So k1 is what? An integer. Therefore we get k is equal to what? 3k1 plus 1. Okay. Now let me say this part, this x is equal to 4k plus 1 as equation number 1. Okay. So now let me write this value of k here so that we will get x there. Therefore equation 1 implies what the 1 gives? X is equal to what? 1 plus 4k. So 1 plus 4k means what? 3k1 plus 1. So this is what? This is equivalent to 5u plus 12k1. So this is same as to say x minus 5u is equal to what? 12k1. Okay. So that is what? 12 divides x minus 5. So this is same as to say x congruence to what? 5u modulo 12. So now these two things are given to us. We have been combined them and we got this congruence. Fine. Hence what can I write? X congruence to what? 5u modulo 12 is equivalent to whom? These two congruences. Equivalent to x congruence to 1 modulo 4 and x congruence to what? 2 modulo 3. These two congruences. This is the answer. As such, we can write a single congruence which is equivalent to two different congruences. Now, let us go for the next one. The next example is that show that 7 divides 3 raised to 2n plus 1 plus 2 raised to n plus 2 for all n belongs to what? Z plus. Okay. So solution here 3 raised to 2n plus 1 plus 2 raised to n plus 2 can be written as 3 raised to 2n into 3 plus 2 raised to 2n into what? 2 square. So this is same as to say this is 9 raised to n into 3 plus 4 into what? 2 raised to n. This can be written as again 7 raised to, this is what? This 3 we will write in different way. 7 into 9 raised to n minus 4 into 9 raised to n plus 4 into 2 raised to n as it is. Okay. So now this is 7 into 9 raised to n minus, I will take this 4 common. It can be written as 9 raised to n minus 2 raised to n. Here this is for all n belongs to set of what? Natural number. Okay. Now this part can be factorized. So this is 7 into 9 raised to n minus 4 into, this is what? 9 minus 2 into another bracket. What can we write? 9 raised to n minus 1 plus 9 raised to n minus 2 into 2 plus 9 raised to n minus 3 into 2 square plus so on up to what? 2 raised to n minus 1. Okay. This can be written as such. Now 9 minus 2 is how much? 7. So this is 7 into 9 raised to n minus 4 into what? 7 into this bracket as it is. 9 raised to n minus 1 plus 2 into 9 raised to n minus 2 plus 2 square into 9 raised to n minus 3 plus on 2 raised to n minus 1 as such. So now from these two terms we can take this 7 common. Why we had did this as such? We want 7 times some multiple here. Then and then 7 can be written. 7 will be what? Divisor of this part. Fine. So this is what? 7 into we get 9 raised to n minus 4 times this. Minus 4 times this bracket. 9 raised to n minus 1 plus 2 into 9 raised to n minus 2 plus 2 square into 9 raised to n minus 3 plus 1 up to what? 2 raised to n minus 1 as such. Fine. So this is 7 into what? K, where K is what? 9 raised to n minus 4 into 9 raised to n minus 1 plus 2 into 9 raised to n minus 2 plus 2 square into 9 raised to n minus 3 plus so on plus 2 raised to n minus 1. This one. Okay. Therefore, and this part obviously belongs to what? Z, as n belongs to set of natural number. Okay. So, now this one we have written as a multiple of 7. So, this gives 7 divides 3 raised to 2n plus 1 plus 2 raised to n plus 2 for all n greater equal what? 1. 7 divides this for all n greater equal 1. Fine. Now, the next example is that next example, what is the last digit? What is the last digit in the decimal representation? In the decimal representation of 3 raised to 400. Now, remember one thing, if in a question, if it is asked for last digit, always take modulo 10 for last digit. For last digit, we should take this one, modulo 10. If for last two digits, the question is about last two digits, then we will take modulo 100. Remember this thing. Always it is asked for decimal representation. Now for last 3 digits, then it will be modulo 1000. Modulo what? 1000. As such, it goes on increasing. Okay. So now we have to determine the last digit for decimal representation of 3 raised to 400. So let us solve that one. Okay. So solution, we have to find last digit. Therefore, that is the remainder of 3 raised to 400 when divisible by what? 10. When divisible by 10. So let A is equal to 3 and M is equal to what? 10. Modulo 10 as I say. So M is equal to 10. So clearly here 3 and 10 are what? Relatively prime. So we can easily apply Euler's theorem. Therefore by Euler's theorem, what we get? 3 raised to 5 of M congruence to what? Congruence to 1 modulo what? 10. Modulo 10. That is 3 raised to 5 of 10 congruence to whom? 1 modulo 10. Okay. So 3 raised to what? 4 congruence to 1 modulo 10. So this is same as to say, this one we get. So this is same as to say 3 raised to 4 raised to 100 congruence to what? 1 raised to 100 modulo what? 10. Okay. So this is 3 raised to 400 congruence to what? 1 modulo 10. Okay. So this shows that 1 is what? The last digit in the expansion. 1 is the last digit in the expansion of what? 3 raised to 400. This remainder is nothing but our last digit here. Okay. Now similar example let me take for last 2 digits. So suppose the next example let me take for last 2 digits. What are the last 2 digits? What are the last 2 digits of the decimal representation of 3 raised to what? 400. So solution: to find the last 2 digits, in the decimal representation of 3 raised to 400 when divisible by what? 100. So let A is equal to 3 and M equal to what? 100. Again clearly here 3 and 100 are again what? Relatively prime. As they are relatively prime, so we can easily apply Euler's theorem. So by Euler's theorem, what I get? 3 raised to 5 of 100 congruence to what? 1 modulo 100. Okay. Therefore, what is 5 of 100? Let us find out 5 of 100. 5 of 100 is what? Now you know 100 can be written as 5 square into 2 square. Already we have done it. So this will gives us, so there is a result to find 5 for this function. So if such a things are there, so 100 into what? 1 minus 1 by 5 into 1 minus 1 by 2. So it will be 100 into 4 by 5 into 1 by 2. So it will be what? 40. This is 10, so get cancelled, 40. Okay. Therefore we get 3 raised to what? 40. Congruence to what? 1 modulo 100. Okay. This gives 3 raised to 40 raised to what? 10. Congruence to 1 raised to 10 modulo 100. Okay. So this gives 3 raised to 400 congruence to 1 modulo 100. Okay. Therefore, what are the last 2 digits here? 1 will be there. So 2 digits are asked. So we can take 0 here. Fine. So this shows I can write lastly, this shows that the last two digits of 3 raised to 400 are what? 0 and 1. Are 0 and 1. This is the answer here. So, as such, these problems will be asked on what? Euler's theorem. So, now here we will stop for the examples. Now, in next video, we will see the linear congruences and some theorems and examples on that. Thank you.